Okay, welcome to the set theory seminar. It's my great pleasure to introduce Sandra Müller. She has given talks in our seminar before, and it's always great to have her. Today's talk sounds super interesting. I think it's the exact consistency strength of AD plus all sets are universally Baire. So go ahead, Sandra. I'm looking forward to that.
Yeah, thank you, Gunther. Yeah, I stopped counting the number of times I've given talks in your seminar. I think it's more than the number that I can count on one hand at the moment. So I think it's fair to stop counting. Okay, but yeah, so today is a new topic. It's different from last time, and I want to start in a similar fashion as I think most of my talks started in the CUNY seminar. So what I want to do today is I want to discuss the deep connection between determinacy and inner models with large cardinals. And so this is based on some older results, and I will lead to a new result towards the end. So we start with discussing games of length omega, and the typical large cardinals that are associated with these kind of games are finitely many woodins. And then we will look at longer games or games on reals. And essentially, I mean, here we have, for example, we have more woodins. Or for games on reals, we actually have, in some sense, stronger woodins than the old ones. I will show you what I mean by that. And then finally, we want to look at determinacy when all sets are universally Baire. And here the large cardinals we will look at are is essentially some cardinal lambda that is first a limit of wooden cardinals, and at the same time a limit of strong cardinals. And we will look at exact consistency statements between these determinacy notions and the large cardinals on the other side. But before we do that, let me start from scratch and let me discuss the games that we want to look at. So as common in set theory, we look at two-player games. We have player 1 and player 2, and they alternate playing natural numbers. And 0 and 1 and 2 and 3 and so forth. So we produce a sequence. And of course, we want to know which of the two players is winning. So before we start playing, we actually fix some set A, which is a set of sequences of natural numbers. So for this talk, these will be the reals. And we say that player 1 wins if the sequence we produced is in this set A. So player 1 wins our game. Let me call the game G of A. So the game is player of set A if and only if the sequence we produce is in A. Otherwise, we say player 2 wins. And we can look at such games for different sets A. And the really interesting notion we want to look at is the notion of winning strategies here. So let me just say it in words, essentially. So we say some function sigma that has as an input some finite sequence of natural numbers, and that gives us a natural number back, is a winning strategy for player 1 in the game G with player of set A, if and only if 1 wins every round of the game according to sigma. So that means player 1 does exactly what sigma tells him to do. So we start with playing just sigma of the empty set, and then player 2 responds with some n1, and then in the next round player 1 just again plays exactly what sigma tells him to do, and now sigma needs as an input the previous rounds. And for simplicity, we can just put all of them. I mean, we just add sigma of the empty set and n1 here, for example, and then 2 responds and so forth. And what we get in the end is always an element of A, as long as we play according to sigma. And there's a similar notion for player 2, where we always get something outside of A. And then we can define the most important notion of today's talk. We can define when a game or a set is determined. So we say the set A or the game G of A is determined if and only if one of the two players has a winning strategy. In the game with payoff set A. And of course, it cannot be the case that both players have a winning strategy at the same time, because we cannot have a run where the resulting sequence is at the same time in A and not in A. But it might as well happen that none of the two players has a winning strategy. This is a non-trivial concept. And before I tell you which sets are determined, let's just briefly look at what determinacy is good for. Yeah, so there are many results that use determinacy and that prove super nice consequences of the axiom of determinacy, meaning that all sets of reals are determined. And I just picked two, one very old one and one more recent one. And there are almost infinitely many that lie somewhere here in between. So these are just to illustrate you some of the useful consequences. So the early result due to Michalski, Sikowski, Mazur, and Davis from the 60s, so almost right after determinacy was introduced, show that what determinacy does is, well, if we have a chaos, we just put everything into order. So we have nice regularity properties. More precisely, if all sets of reals are determined, then all sets of reals are Lebesgue measurable, they have the Baire property, and they have the perfect set property. So we have all super nice structural consequences that we can think of for sets of reals. And another result is something from general topology, for example. Also the statement has nothing to do with games, for example. So these are really questions that you can just ask, and it turns out that the answer depends on the axiom of choice or on the axiom of determinacy. And for this result, for example, we proved that if all sets of reals are determined and X is a zero-dimensional homogeneous space that is not locally compact, then X is strongly homogeneous. So for today's talk, it doesn't really matter what these notions are. I just want to illustrate that determinacy can be used to prove things outside of set theory and outside of the world of games and whatever. So it really has structural impact on the real line, or the sets of reals and the real line there. And even nicer, all of these results have local versions. So the way I stated them, they suppose the full axiom of determinacy. If you don't like that, what you can also just say is you can, for example, say if all Borel sets of reals are determined, then all Borel sets of reals are Lebesgue measurable, have the Baire property, and have the perfect set property. This is not even the optimal result that I just stated. But we can restrict ourselves to nice point classes and look at determinacy for these point classes. And for such nice point classes, determinacy is actually something that we can prove from the standard axioms that we like. So which games are determined? Let's work in ZFZ. And the very first result, both in order of consistency strength and in chronological order, is due to Gale and Stewart and was proven already in the paper where they introduced determinacy. And they showed that every open and every closed set is determined. And now, so when we go downwards, this is the order in consistency strengths. Not in chronological order. The next question would be, okay, now that we know that open and closed sets are determined, how about combinations of these, and ultimately how about Borel sets? And Martin managed to prove in 1975 that every Borel set of reals is determined, just in ZFZ. Okay, so now that we know it for Borel sets, the next question is, okay, what happens for analytic sets? So analytic sets are projections of Borel sets. It's the most natural next point class to consider. And Martin proved in 1970 that every analytic set is determined given that there is a measurable kernel. So here there's something in the hypothesis, but at least we get the consequence we want. We get that every analytic set is determined. And this picture continues. So Martin and Steele proved, for example, in 1985, a determinacy for sigma 1 n sets. So these are sets in the projective hierarchy. And we can obtain them from analytic sets by taking complements and projections. So it's just, we essentially take the same operations that gave us analytic sets from Borel sets, and we built a hierarchy using this operation. And we can get that these sets are determined if there are n wooden kernels with a measurable kernel above them all. So again, we have an hypothesis that is beyond that of Z, and that's even stronger than the measurable kernel we had earlier. And there are many more results that sit somewhere here, for example. And also there are some results that sit here. This is not the full picture, but ultimately we have something like 0 equal 1. So in Z of Z, there is a non-determined set. So of course, the natural question is this actually necessary? Are these large kernels necessary for the determinacy of these sets of reals? Maybe the proofs are just not the optimal ones. Maybe they're better proofs, and this happened in the past. I mean, some of these results were proven from stronger large kernel hypotheses. And for example, if you assume a supercompact, it's much easier to prove determinacy than if you just assume a measurable or finally many wooden kernels plus a measurable on top. And if you don't ask for the optimal result, it's easier. But of course, I mean, where do we stop? Right? We want to know whether these results are actually optimal. And the answer to this question is in some sense. So I will give you some more details on the following slides, what I mean by that. And it's related to the next question. So how can these large kernels impact what happens with the sets of reals? Let's look at the universe of sets. Let's draw V, and we have the ordinals somewhere here. And if we think about determinacy, it's all about sets of reals. So this is where determinacy happens. It's very low in the large kernel hierarchy. And then we have these large kernels. They're very high. Yeah? I mean, that's the way we have some kappa. That's a measurable kernel. Or we even have, say, maybe a wooden kernel somewhere here. And they're very high in the large kernel hierarchy. So how can it be that these large kernels have an impact on what happens with sets of reals? Yeah, I mean, it's kind of strange. You have these kernels here, and they have the sets of reals down here, and how can these actually even relate to each other? They're so far apart in the large kernel hierarchy. And the answer sits here in the bottom of the slide. The answer is that this is not really how the picture looks like. So what it does have an impact on determinacy is not the large kernels themselves. It's mice, so say some nice inner models. With large kernels. And the nice thing about these inner models, or one of the nice things, is they're countable. So these mice, they sit on the same level as the determinacy questions we asked. They are very low in the hierarchy in our universe of sets. And I will show you on the next slides how these things are connected, and why this is what we should look at, essentially. So let's be a little bit more precise. The first result in this direction is a well-known equivalence for analytic determinacy. That's due to Harrington and Martin. And they showed that it's equivalent that all analytic games are determined and X sharp exists for all reals X. So what is X sharp? Let me just draw a picture. We have some real X at the bottom. And what we do is we build something like L of X. So we have a nice hierarchy, we have a nice model there. And in addition, we have something that we call the top measure. That's what the sharp stands for. So this is our sharp. And it's in some sense just a trace of a measurable cardinal. So this is the canonical inner model for a measurable cardinal, and this is really what Martin used in his result. I mean, I proved earlier, or I stated earlier, that Martin showed that if there is a measurable cardinal, then all analytic aims are determined. But if you look at the proof closely, then you see that actually this here is all he needed. And Harrington showed that this is optimal. So we do have an equivalence there.
I mean, maybe because that, like, if you think about it in the sense of, if you were trying to turn this argument around that gave you determinacy of analytic sets from a measurable cardinal, and you wanted to get the measurable cardinal back, of course, there's no way to do that, because you could just, collapse the measurable cardinal to omega-1, and you wouldn't destroy the axiom of determinacy, right? I mean, the determinacy of the relevant set. So yeah, it's kind of, it makes sense that these mice are countable structures, right? So they are at the right level in a sense when you think about it in terms of what could the equiconsistency look like.
Yes.
Right.
Yeah, exactly. I mean, if you ask for an equiconsistency, or even, I mean, these are equivalences. Yeah? I mean, this is even more than just an equiconsistency, and it has to be something countable. Yeah, it's just. I mean, for me, it was a bit frustrating when I was even like what a graduate student, an early graduate student. I started looking at these results. I found it strange that I mean, if you look at them in graduate textbooks or in most of the books that I looked at that time. It all looked like, okay, you have the large cardinal and then you have determinacy, and it looked like this is the result you should aim for. And as you just said, this doesn't make any sense if you think about it closely. And I mean, I've even talked to senior colleagues that still, I mean, that just didn't think about this deeply enough, I think, to see that this just doesn't make any sense. And this is why I'm putting an emphasis on this. These are countable models, and it's all it does make sense. Yeah, I mean, inner model theory is somehow sometimes deemed to be very complicated, and I've had many people telling me that they don't understand what's going on, and it's all somehow a mystery. But as you just said, it's not really a mystery because it has to look like this. Yeah, there's a good reason why we have to look at countable models, and there's a good reason why these are the right models. So yeah, in some sense, this is also a talk as an advertisement for inner model theory. Yeah, is there a question?
Sandra, the consistent X sharp exists for every X is much weaker than a measurable, right?
Yes.
Ramsey already implies that.
Or omega-1 R dash.
Oh, already. Oh, yeah. Already omega-1 R dash. Yeah. Okay.
Mm-hmm. Yes, and I think there's another question, but I cannot hear you. I think you have to unmute yourself.
Oh yes. About the countable models. I mean, as I remember, the first mouse was actually appeared in Geismann's paper, where he took a countable model with a measurable cardinal and iterated it beyond its ON, and proved there were only, then proving they were getting a truth definition for L, and showing that there are only countably many constructible reals. Is that still the folklore, that that's the first mouse?
So I don't know the history well enough to say that this is the first one, but it does sound like a mouse to me, and so I guess you're right.
Well, I mean, it's because you're talking about these countable models, and that was the key thing in Geismann's construction. Yes,
I mean, so the notion of mouse changed during time. I mean, the first models really looked like L, and they had a measurable cardinal. And the way we understand these mice changed because it turned out that it makes sense, for example, to also add partial measures to the sequence. And so this was done by Ronald Jensen mainly, and many others. And so with these kind of mice, So actually, so for this picture here, it doesn't make a difference which type of mouse you look at. I mean, it's perfectly fine to just think about the model where you have this one measure in some sense. But for the next slide,
sorry.
Projective determinacy, we need much more. Yes?
But I mean, it's just a predicate for the measure, right? So it's not an element of the mouse. So it's right. And so there is still a subtle difference between a model with a measurable cardinal and this X sharp, right?
Yeah, sure. But it's I mean, still. So for example, if you look at this, I mean, you have this one predicate for the measure, but there's not a very complicated sequence of measures, for example. Yeah, so this is what I meant. I mean, here you don't have to think about the structure of the model that much.
Yeah, and it's also total and everything.
Yes.
The measure, I mean, yeah.
Yeah, and I mean, this works perfectly fine if you have finitely many measurable cardinals that you want to consider. But if you want to look at more complicated structures, for example, I mean, the latest when you learn to look at wooden cardinals and also patterns of strong cardinals already, then what you should do at least is you should add partial measures to the sequence, and you get a very complicated structure. But the idea is still the same as you have for L. Or maybe, I mean, I mentioned Jensen already. I mean, what I should really say is J of X. Yeah? So whenever I say L, I really mean J in the J hierarchy that is due to Jensen, because this is what is both customary and useful in inner model theory.
May I make a quick comment about this work of Geifman that Ken was mentioning? So Geifman was working with these ultra powers, but if I remember correctly, it was Rowbottom who first pointed out the consequence that there are only countably many constructible reals.
I see.
Of cardinal.
Rowbottom drew that conclusion from a Ramsey cardinal. It didn't have to be measurable, only had to be Ramsey.
Okay, thank you.
Yeah, thank you for these comments. This is very interesting. Okay. So now, when we look at, wait, Russell, is there a question? I can see you're saying something, but I wasn't sure whether you, no? Okay. Okay, so when we look at more complicated models, we also get an equivalence for projective determinacy. So, I mean, I don't want to go into the details, but the idea is very similar to the one on the previous slide. So the statement also looks similar. We look at the level of the projective hierarchy. We have sigma and n+1 determinacy. And now we get a model that is our canonical models for n wooden kernels and a measurable on top. So here, it looks very similar. We start with this real X, and we also have this top measure, the sharp. But in addition, now the model thinks that it has n wooden kernels. So they sit somewhere here. And this model has a more complicated niceness property. So for example, we say that it's omega-1 iterable, whatever that means. Yeah. But still, it is a countable model. And it's a model of the statement that there are n wooden kernels, and it's in some sense minimal with this property. And again, we have that for every real X. And these two statements, again, are equivalent. But it took much longer to prove these kind of results. And you have to look at more complicated models. And these models, for example, as I already mentioned, they have partial extenders on their sequences. And they're very rich to back up these wooden kernels in some sense. Okay. And we can actually draw this picture a bit further. And for example, when we can look at games of countable length alpha bigger than omega. Yeah, I mean, currently we look at these 2-player games and we have n0, n1, and so forth. But why should we stop playing at omega? As set theorists, we can just keep playing and let player 1 start another round with n omega, and then we have n omega +1, and so forth. And we can continue like this for any countable ordinal alpha. So before the beginning of the game, we fix some alpha. And we say, okay, we look at a game with alpha many rounds. And if we suppose that these games are determined, so this means a game with omega times omega plus n many rounds. And the payoff, let's say here is pi11 again, or just analytic. Then we can prove that there's a mouse. So a nice model with omega plus n wooden cardinals. And Itai Neyman showed that this is the right number of wooden cardinals you should expect. He showed that if you have omega plus n wooden cardinals in a nice countable model, or you have omega plus n wooden cardinals plus another measurable on top, then you do get that these kind of games are determined. So this is the exact number of wooden cardinals that we would expect here. And there are similar results for games of length omega times omega to the alpha. So for additively indecomposable ordinals, Nam Truong showed in his PhD thesis that also there you can get a mouse with the expected number of wooden cardinals back, omega to the alpha in this case. And you can actually combine these two techniques. And if you look at games of length omega times omega to the alpha plus n, so you add finitely many rounds in the end, then again, you can get omega to the alpha plus n wooden cardinals back. This picture that started essentially with Harrington and Martin can be continued, and we do understand at least almost how strong the determinacy for these kind of games is. And we can even do it for games on reals. So this is similar than before, but now instead of playing natural numbers, we allow that the players play real numbers. So player 1 plays some x0, and then player 2 plays x1, and so forth. And now our payoff set A is just, instead of a sequence of natural numbers, it's just a sequence of real numbers. And we can again just ask that what kind of sequence we produce, and whether this sequence is in this set A we started from or not. And we also sort of understand how strong the determinacy for these games is. For example, it's equivalent to have projective determinacy for these kind of games on reals, and that Mn sharp of R exists for all natural numbers. So this looks similar than the Mn sharp of X we had before. We again have the top measure R sharp. We have n wooden cardinals. But now instead of constructing from some single real X, we start with all the reals. This model is no longer countable because we start with all the reals. But it doesn't really increase in size from the size of the reals. So it does look different. This is, for example, what I mean by these wooden cardinals are in some sense stronger. Yeah, I mean, it's stronger to be a wooden cardinal in this model than to be a wooden cardinal in the model where we start from the empty set. Because we have this X of banks here, and this model contains all the reals. Yeah, I mean, this is not a model that has only countably many reals from the outside, but still, this is a very nice canonical model, and this is the one we should look at if we want to analyze the determinacy for games on reals. So this is one line of research. We can just look at more complicated games, and we can look at longer games. We can even look at games of length omega1 and try to understand the determinacy for these games in large cardinal strength. But there is another approach. And this is another approach that will help us understand the inner model problem better. Yeah, I mean, so what we're aiming for is we want to construct stronger and stronger inner models and really understand how these two concepts relate to each other. Yeah, determinacy and large cardinals are coming from completely different areas of set theory originally. And I believe that it's very interesting, and that it's a very deep result that they are so tightly connected. And another way of looking at this connection is by keep playing games of length omega, but imposing additional structural properties on the model. Yeah, so now we look at the axis of determinacy on the same games of length omega than we started with, but the models are different now. So what do I mean by this? one thing we can look at is we can, for example, look at Suslin sets. So being Suslin is a generalization of being analytic. Being analytic just means to be a projection of a tree on omega times omega. So we have this, and being Suslin just means the projection of a tree on omega times kappa for some ordinal kappa. So A is the Suslin set of the projection of the set of branches for some such tree T. And at the axiom of choice, this is not an interesting concept. And at the axiom of choice, every set of reals is Suslin for a tree on omega times the continuum. But under the axiom of determinacy, which, as we've seen at the very beginning of today's talk, contradicts the axiom of choice, this becomes a really interesting property. So there are natural models in which not every set of reals is Suslin. For example, L of R, if it satisfies the axiom of determinacy. So this becomes a non-trivial concept. And to give you an idea what this concept is, let's look at the following result from due to Martin and Wooden from the 80s. So if we're living in our world with the axiom of determinacy, so all sets of reals are determined, the following are equivalent. ADR is equivalent to all sets of reals as Suslin. So ADR just means that all sets, let me just say all games on reals of length omega are determined. So these are games on reals just as on two slides ago. And this shows already that the assumption that all sets of reals are Suslin is very strong together if it's paired with the axiom of determinacy, because it already gives us determinacy for games on reals. So this is just to give you some intuition about this hypothesis that all sets of reals are Suslin. And now we can look at the large kernel strength of this hypothesis. And so one direction was shown by Wooden with this famous derived model construction, a variant of that in the 80s already. So if there's a kernel lambda that is the limit of Wooden kernels and limit of less than lambda strong kernels, then there's a model of AD plus all sets of reals are Suslin. And let me just draw one picture how a typical model would look like. In case you've seen these extended pictures before, this might be helpful. So we have this kernel lambda, and this is the limit of Wooden kernels. So we have all these Wooden kernels here. And now in addition, it's a limit of less than lambda strong kernels. So these sit somewhere here. What does it mean to be less than lambda strong? It means that the critical point can be pushed very high, but arbitrarily high below lambda. So if we draw them as extenders, they look like this. So we have a lot of extenders witnessing that these kernels are less than lambda strong, and they are very overlapping because we keep overlapping these Wooden kernels, as lambda is the limit of both the less than lambda strongs and the Woodens. And this is what makes the model very complicated. This is what gives its strength. But we always stop below lambda. So this is the typical picture for such a model. And Steele showed in 2008 that this is optimal. So if there is a model of AD plus all sets of reals are Suslin, then there is an inner model that has that looks like this. And that's this large kernel pattern. Okay, so what happens if we look at something even stronger? A canonical strengthening of being Suslin is being universally Baire. Now, being Suslin means to be the projection of a tree, and being universally Baire means to be the projection of a very nice tree. So what is a very nice tree, in my sense? Let's say that a pair of trees S and T on some omega times kappa for some ordinal kappa is absolutely complementing, or more precisely Z absolutely complementing for some set Z. If in every generic extension collapsing Z to be countable, the projection of S is still the complement of the projection of T. So this has two parts. The first thing is that the projection of S and the projection of T are still disjoint. And the second part is that they still union up to all the reals. I mean, here the first part is easy, and this is just by absoluteness, and this is the interesting thing. So the interesting thing is that in the extensions, the trays don't get too thin, and they still, if we look at the union, they still cover the whole space. And being universally Baire, and this is a notion that goes back to Fang, Magidor, and Wooden, means that it's the projection of a tree that comes from some absolutely complementing pair. More precisely, so a set of reals A is universally Baire for every such set Z. There are Z absolutely complementing trees S and T such that the projection of S is equal to A. And again, this is a very interesting notion now, even under the axiom of choice, because not every set of reals is universally Baire. And you can, for example, show that universally Baire sets have regularity properties like Lebesgue measurability and the Baire property. And so it cannot be that under the axiom of choice, all sets of reals are universally Baire. So how strong is this when it's paired with determinacy? Paul Larsen with Grigor Sargsyan and Trevor Wilson showed, I think around 2014, and maybe Paul, you can correct me if this number is wrong, that if there's a cardinal lambda that is a limit of wooden cardinals and a limit of fully strong cardinals, then there's a model of AD plus all sets of reals are universally Baire. And they conjectured that this is optimal. Yeah, so it felt like this might be the optimal assumption, but of course they couldn't prove it at that time. And now the good news is that the answer is yes. Yes, so the conjecture holds, and this is actually optimal. So let me just rephrase the statement. Suppose there's a model of AD plus all sets of reals are universally Baire. Then there is a model of ZFZ that has a cardinal lambda that is a limit of wooden cardinals and a limit of fully strong cardinals at the same time. So how does this look like? If we look, so we have a similar picture as before for Wooden's derived model result that still proved is optimal. We have a cardinal lambda, and that is a limit of wooden cardinals. So we have our wooden cardinals here. And at the same time, this is the limit of strong cardinals. So we have strong cardinals. And these strong cardinals are in particular less than lambda strong. So we have all these extenders witnessing that we can push the critical point somewhere here below lambda. But now these are fully strong cardinals. So they're actually even overlapping lambda. And they're going all the way, even out of the slide. Yeah, so these cardinals are fully strong. They are strong throughout all the ordinals. And this is what turns this model into a much more complicated model, because the extender pattern it has to witness these large cardinals is more complex than the previous one. So how do we prove this result? How can we show that if we suppose there is a model of AD plus all sets of reals are universally Baire, then we can construct such a model. And this model will actually be a mouse. So it's a canonical inner model, like the ones we've seen at the beginning of the talk. Okay, so let me go into some ideas behind the proof, and I will be very vague, but I hope that I can give you some sort of intuition. And the first thing we need to look at is what John Seals calls the triple helix. So what happens is that we now need to look a bit closer at the connection between determinacy and inner models with large cardinals. Yeah, I mean, we've studied this connection for the last 45 minutes, but now it becomes a third component. We add a third component to it. And the third component are hybrid mice. So what is a hybrid mouse? Well, in words, it's something, I mean, in the picture, you can see it's essentially a mouse that has the features of lions. And this is exactly what happens in some sense. Yeah, so it's a mouth with extra strength. And the extra strength is coming from iteration strategies. So I think the idea of looking at these kind of models is due to Wooden, and it was fully done by Grigor Sargsyan, essentially in his PhD thesis. So how do these models look like? Let me just draw a very big universe here, and we have our ordinals, and the typical mice we want to look at, they will have Wooden cardinals, right? I mean, we want to have a limit of Wooden cardinals in the end. So let's say they have some delta 0, delta 1, delta 2, and so forth. So these are Wooden cardinals. But now we need something in addition. And in addition, they will have a predicate for iteration strategies. So for example, here at delta 0, we have some sigma 0, and this is an iteration strategy for the model up to this level. And we will add this as an extender predicate here in the model while we construct it. So we have extender predicates, or we have a predicate for the extender sequence that will witness large cardinals directly. And we have another predicate that will add this iteration strategy, and this will give us a different sort of strength. And so here we have another strategy, sigma 1, and we will add that and so forth. So the model will be even more complicated than before. At the very beginning, we started with L, and then starting from these X sharps and going through these MN sharps, we've seen that we need to add extenders in order to witness large cardinals in the model. So first it was just one extender or even a measure, and then it became an extended sequence. And now we do something even more complicated, and we even add some iteration strategy, or we can think of this as a sequence of strategies. Yeah, so the model becomes more and more complicated. And this is no longer an ordinary mouse. And so this is what it's called a hybrid mouse. It's a hybrid structure because in addition to the extender sequence, it also has these strategies as a predicate. And if we look at this, we can build the triple helix, because what we're actually still interested in is our connection between determinacy and large cardinals. Yeah? I mean, we had determinacy here, and we had mice with large cardinals. And now we have the third component, the hybrid mice. And what we want to study is the relation between these two things. And for the lower levels in the large cardinal hierarchy, we have seen that we can directly translate between these two objects, yeah, or these two hierarchies. Yeah? I mean, each of the 3 points here is actually a whole hierarchy. And now we want to look at the statement where here we have AD plus all sets are universally Baire. And here we want to have our lambda that is a limit of Woodens and Strongs. And we want to go from here to here. How do we do this? Now we go through these hybrid mice. So we use our determinacy assumption to construct a hybrid mouse. And once we have the hybrid mouse, we will translate it into an ordinary mouse. So there's something that's called a translation procedure here. And this part will be done by something that we call hot analysis. So to prove the implication from here to here, what we do is we go through these kind of hybrid mice. So let me say a little bit more about this. So as I said, the proof splits into these two parts. We have the hot analysis to get a translatable hybrid mouse, and then the second part is to actually translate our translatable hybrid mouse into a mouse with large cardinals. So for the hot analysis, what we do is we analyze the minimal model of AD plus all sets are universally Baire, and we consider it as a direct limit of so-called hot pairs. So this is essentially standard. I mean, there are some things to be careful about, but this is these hot pair constructions and this hot analysis in general is well known, and it goes back to wooden and steel, but then also Grigor Sargsyan and Nam Trang and many others have shown that these constructions work in different settings. And the really key new part is the second one, that we have a translation procedure. So we have the hybrid mouse, and what we want to do now is we want to translate the iteration strategies into strong cardinals. Because remember, we want to have the model with some lambda that is a limit of wooden cardinals. Yeah, but we will have the wooden cardinals essentially for free. The key thing is to show that they are strong enough to survive, that we, in addition, can put the strong cardinals here. So in written, this is what the translation procedure will be. So it's an extension of work of Steele, Yijing Zhu, and Grigor Sargsyan. So Steele and Zhu had translation procedures that worked in a specific context, and Grigor had one that works in this general context, but that only produces a single strong cardinal and not a limit of strongs as we are aiming for. So what we prove is that if we start with a suitable hybrid mouse, then the result of our translation procedure is an ordinary mouse. So just one with an extender sequence. It looks like some with some extender sequence that has a cardinal lambda that is a limit of wooden cardinals. And in addition, a limit of fully strong cardinals. And as a bonus feature, it will actually be a mouse. So Grigor's construction doesn't give an iterable model, but ours does. So all hulls of our model are iterable, and this is what turns the model into a mouse. And so I needed to prove that it's a mouse because I needed to use the iterability in the proof that these strong cardinals are really fully strong. But it's an additional nice property to have in the end, because if you think about further applications of this translation procedures, apart from this one result on the consistency strength of all sets IUB, then this is something very useful to have. And this is really what turns the nice countable models into these very strong mice that have additional features. Okay, so I briefly want to tell you how the translation procedure is defined and why it works, but here I will have to be very sketchy, but I want to give you at least a general idea of what happens. So we start with this model that has these strategies, and how do we translate the strategies into large cardinals? Now there are two different things we need to take care of. the first thing is we want to make sure that we preserve the wooden kernels. Yeah, so we need to have our limit of wooden kernels in the end. And we do this by something that's just called a standard fully backgrounded construction. So the model is built inductively. So we build it level by level, and we take cores at each step. So this is a technical detail that if you haven't seen these constructions before, I think would be too much to go into. But this will ensure that we will get a nice fine structural model, right? I mean, we want to have a model that has essentially the same properties as L. And for this, it's important that we maintain this fine structure. And this is a way of doing this that's very canonical and that's well known for many years now. And so the first thing is we want to maintain the wooden kernels. And the way we do this is we add all fully backgrounded extenders. So essentially the idea is we work on the hybrid model, and whenever we see an extender that is an extender on our sequence, then we more or less add it to the new model as well. So these extenders used to witness woodenness in the hybrid model, and they are going to witness woodenness for the same kernels in our translated model. And preserving wooden kernels this way is completely standard, and it's I mean, it's very powerful of this construction, but this is nothing we need to worry about. The thing we need to worry about is more is that we want to have strong kernels. And for these strong kernels, so let's say these wooden kernels are called delta I for just natural numbers I. For the strong kernels, the one we will look at are the ones that are strong up to the next wooden kernel. So we say let kappa I be the least less than delta I plus 1 strong cardinal. So we take canonical candidates. If we look at the model, we have, let's say we have delta 0 here, and then we have delta 1. And somewhere in between here, we have kappa 0. So it's the one that is strong up to here. So it already has extenders that go up to delta 1. And what we need to show now is that it also has additional ones that go past delta 1, actually past everything, that go throughout the ordinals.
Sorry, Sandra, what do you know about the hybrid model that you're working in? What it has cardinals that are strong up to the supremum of the woodens, or
no?
no?
So the only thing I know is that it has a limit of wooden cardinals. These are the delta 0 delta 1s. And I look at the ones that are strong, so the least ones that are strong up to the next wooden cardinal. Yeah, I mean, delta 1 is a wooden cardinal.
Cool. Sure. Yeah, sure. I just forgot the context. Yeah, definitely. There are many that are strong up to that. Yeah, sure. Okay.
By the definition of wooden kernel that I didn't give in this talks.
No, but I just was, I kind of forgot what we assumed about this hybrid mouse. So yeah, okay, thank you.
And I mean, I didn't say it precisely because, I mean, to give you the precise definition of the translatable structure, I probably need like 10 pages or something like that, because, I mean, what we want is we want to have that it has nice iteration strategies. And one thing is that these iteration strategies need to be universally Baire. And this is where we're using that the background is satisfies that all sets of roots are universally Baire. And there are many other, I mean, mostly well-known properties of iteration strategies that you want to have in these hybrid models. And these properties will allow us to do the translation procedure in a way that I'm describing now. But I mean, to make sure that we are not sitting here until tomorrow morning, I mean, at least tomorrow morning, my time.
Sure. No, it's fine. That's
Many of the
fine.
details. So, I mean, it's good that you're asking. And if you have more questions, I mean, please ask, and I'm happy to give you some more details. But yeah, this is exactly the picture you should have in mind. I mean, we have a model that has this limit of wooden kernels, but essentially nothing more in the large kernel sense. So we only suppose that we have strongs that are strong up to the next wooden kernel. And this is automatic. So what we need to do is we need to add the extra extenders. Yeah, I mean, we need to make sure that we can add extenders that witness strongness past the next wooden and even past the limit of woodens. Yeah, I mean, it needs to go all the way wherever, yeah, up to here. And the way we do this is we identify a nice property of extenders that allows us to add these extenders in some sense. So what we want to do is we add all generically countably complete extenders with critical point some such kappa I. So the kappa i's are going to be the strong kernels, and being generically countably complete means being countably complete in all generic or small generic extensions, so below the critical point. The reason why we look at countably complete extenders is that this will allow us to prove iterability of the model we construct. And this is actually the full definition of the translation procedure. And in some sense, it's a bit cheating because it's hiding a lot of details, because what we actually do is, when we prove that these generically countably complete extenders have very nice properties, and we can identify them or characterize them using the iteration strategies. So the idea is that these extenders are characterized by the iteration strategies sigma I that we have in the hybrid model. Yeah, so this is what I mean by translating the strategies into strong kernels. We do have these nice strategies, and we ensure that the extenders we add are given by the strategy. So essentially, the outer power embedding by the extender is the same as the iteration strategy that is given to us by the strategy sigma I. And there's a way to make this precise. And if we have the strategy, we can prove that the strongs up to the next wooden kernel are actually fully strong in the model.
Could I ask again, this construction of the translated structure, does that happen completely inside the hybrid mouse, or are these? Yeah. Okay. All right.
Yeah. Yes. And I mean, the nice thing about defining it this way is that I mean, once you know what the hybrid mouse is, the definition of the translation procedure is very easy. I mean, the previous translation procedures, for example, I mean, this one is more closely to Grigor's one than to the one by Steele and the strengthening of that one by Zhu. And this translation procedure is actually, Grigor's one is very complicated to define, because you need to first say what you mean by characterized by the iteration strategies. And you need to make that precise in order to define the translation procedure. And the nice new thing here is that we can actually just do it for these kind of extenders and prove that they have the nice properties. So the translation procedure becomes very easily definable. And I mean, mathematically, it doesn't really make a big difference, but it's just nicer to have. And I mean, if I want to be really honest, it's probably, I mean, maybe this would even be the better definition, because you would see directly why this is working. But this is easier to understand and to define. So, and we need it. I mean, we need this extra property for the iterability anyway. So, I mean, I like to phrase it like this because I feel like it's easier to at least define the procedure. What is the idea? I mean, how do we prove that it works? So we are now just jumping towards the very end of the argument. And say, suppose it doesn't work. So suppose not. Say we have some kappa I that is not fully strong. So we have our model M. This is the one we constructed. And we have some kappa I here, and we have some xi that is not, kappa I is not xi strong. And this was constructed inside this hybrid W. Okay, so what do? We take a hull of this situation, and we get a small model M bar, and we get some W bar. So this is of size above kappa I degrees, actually, up to kappa I. And it's of size below the next wooden cuddle. I mean, let's say delta I+1 is somewhere here. And so this model has some pre-image of xi, some xi bar that is not overlapped here. What we do is we compare. I mean, now we use the fact that hulls of M are iterable. Yeah, I said this is why we want to look at generically countably complete extenders, and this is where we are using it. So we can compare M bar against the construction of M, and we obtain some iterate here. This is still small. Let's call it M star. So this will still be below delta I+1. And we can prove that actually in the comparison, and this is now where all the technical things go into. I mean, so this part of the argument is non-trivial. We prove that in the comparison, I mean, first of all, the M side here never moves, the construction of M. And in this part from M bar to M star, we have a non-dropping iteration. So we have an iteration embedding here with critical point above kappa I. And notice that this is not trivial because we might have extenders that are overlapping kappa I here. So we need to prove that we never use these extenders. And the reason is we never use them because they look exactly the same here and here. Because we know that they all come from the strategy. We know that they all come from the sigma I, so they're going to be the same. This is the idea here. And but now, I mean, we have this model M star, and we show, let's say this is some I, that since this is all below delta I+1, there's an extender here, let's call it F, that overlaps xi bar. Xi bar is very small. We collapse the model below the size of delta I+1. And what we prove is that we can actually use the embedding I to define an extender here. And now this extender overlaps xi bar, but we assume that this is witnessing that kappa I is not xi bar strong in M bar. And this gives us a contradiction. So E contradicts that xi bar is not, oh, sorry, that kappa I is not psi bar strong in M bar. And this is the main idea. So it all boils down to this comparison argument. And we use the fact that the extenders are coming from nice strategies, and actually all extenders, all relevant extenders are coming from nice strategies, in order to prove that this comparison actually has a very nice structure, and it's very simply to understand. It's very easy to understand. Okay, so let me sum up again what we've done. So we've looked at the deep connection between determinacy and inner models, and we also looked at the third component, these hybrid mice that have the extra iteration strategies. And using these ideas, we obtained the following corollary. So this is the new translation procedure together with Larson, Sargsyan, and Wilson's result. The following theories are equiconsistent. That F plus the axiom of determinacy plus all sets of weights are universally Baire, and Z of Z plus there's a limit of wooden cardinals that is at the same time a limit of fully strong cardinals. And thank you. This is all I wanted to say.
Thank you. Great. There were a lot of questions already during the talk. I'm sorry about that.
Feature of the set theory seminar, right? I would have been disappointed without it.
Actually, can I ask another thing? So in this translated mouse where you have that this limit of wooden cardinals is also a limit of strong cardinals. So what is that a ZFC model?
Yes.
Okay, so, okay, great. So, yeah, because I was trying to understand how high the ordinals are. Okay, so you have a ZFC model with where all of these are strong. That's
Yes,
cool.
I mean, if you start with the proper class model of ZF plus AD plus all sets of weights are universally Baire, you will get a proper class ZFZ model with this unique, or with this, yeah. So,
Right.
whatever unique cardinal lambda saying that that is a limit of wooden cardinals and a limit of fully strong cardinals. Yes.
I was just thinking because I feel like it's relevant to say that, because otherwise, you know, it could be that it's just a mouse, whatever, that has maybe I mean, so to speak, when it's a ZFC model, that means its ordinals are fairly closed in a way. So it's nice that you get such a model.
Yeah, I mean, you can construct it in a way that it just contains all the ordinals. Yes.
Great. Are there any further questions for Sandra? Let me maybe remove the spotlight here. Okay, any other questions? Okay, doesn't seem so. Well, I thought that was a super interesting talk. Thank you so much, Sandra, and congratulations. It's a great result.
Thank you. And thank you for your interest.
Okay.
Okay.